Hello everyone. Let us learn one of the important property of topology. If we are considering two topologies, say tau1 and tau2, then their intersection is also a topology on X. That is, the intersection of two topologies on a set capital X is a topology on X. Let's prove this. Let us consider two topologies tau1 and tau2 on X. Then, as we know by the definition, X comma empty belongs to tau1 by first property of topology. Similarly, X comma empty belongs to tau2 because tau1 and tau2 be two topologies on X itself. Therefore, we can write X and empty both belongs to tau1 as well as tau2, that is tau1 intersection tau2. Let us consider the collection G lambda, where lambda belongs to index set, be the members of tau1 intersection tau2. Then G lambda, provided a lambda belongs to index set, is a member of tau1, and G lambda, provided a lambda belongs to index set, is a member of tau2. Because G lambda is a collection, be a member of tau1 intersection tau2. Here intersection is there. Intersection implies this member belongs to tau1 as well as tau2. So G lambda is a member of tau1 and G lambda is a member of tau2. These two collection. As we know, tau1 and tau2 both are the topologies on X. Right. So since tau1 and tau2 are topologies on X, union of G lambda, provided lambda belongs to index set, be the element of tau, that is union of members of tau is a member of tau, that is by the definition of topology. Union of members of any subcollection of tau is again the element of tau, right? Similarly, union of G lambda, where lambda belongs to index set, belongs to tau2 by the definition of topology. As we got union of G lambda belongs to tau1 as well as tau2, we can write union of G lambda, provided a lambda belongs to index set, belongs to tau1 intersection tau2. That is the arbitrary union of members of tau1 intersection tau2 is a member of tau1 intersection tau2. So this is the second property, and we need one more property which is for intersection. Let us consider two arbitrary elements of tau1 intersection tau2. So let A and B be any two elements of tau1 intersection tau2, which implies A and B belongs to tau1 as well as AB belongs to tau2. Therefore, A intersection B belongs to tau1, since T1 and T2 both are independently topologies on X. So A intersection B belongs to tau2 itself. Combining these two, we get A intersection B belongs to tau1 as well as tau2. This proves that the arbitrary intersection of any two members of tau1 intersection tau2 is a member of tau1 intersection tau2. Therefore, by induction, every finite intersection of members of tau1 intersection tau2 is a member of tau1 intersection tau2. By all the above three results, we can tell that tau 1 intersection tau 2 is a topology on X, because it satisfies all these three conditions. That is, X and MT belongs to tau 1 intersection tau 2. The first property we have proved this, and second one is the arbitrary union of members of tau 1 intersection tau 2 is a member of tau 1 intersection tau 2, the second property. And the third property, which is finite intersection of members of tau be the member of tau itself. So by all these properties we can prove that the intersection of two topologies on X is a topology on X.